Welcome to the webinar tonight on amateur-built aircraft certification. This is a case study. There was an application submitted and it was denied. It was not submitted to the San Antonio FSDO, but it is still a good educational opportunity. And my name is Gary Mitchum. I'm the Airworthiness Fast Team Program Manager for San Antonio. And Ryan Newman is my cohort here. He is the operations FPM for San Antonio. And this is worth 1 credit for basic knowledge topic 3, and it's also worth 1 hour of AMT credit. And here's the slide I should have had up. It says, if we do have technical difficulty, I will try to resume as quickly as I can. If I can't resume the webinar, it will be rescheduled and you'll be notified through our SPAN system or a direct emailing if possible. Also, the regulations referenced in the presentation might be abbreviated or paraphrased just for brevity and clarity. So if you have a question about a regulation, it's best to always look up the full regulation. Okay, it's saying that the chat is disabled, so I'm going to see if I can fix that. I don't see that function here unless it was disabled during the creation of the presentation. I don't see a functionality where I can enable the chat, unfortunately. So a little background information: an application for a special airworthiness certificate was received for a Bear Hawk Patrol amateur-built aircraft. And an FAA DAR performed an inspection of the aircraft, but due to multiple discrepancies, the application was denied. Here's a blank sample of the 8130-6, and AC 21-12 provides instructions to applicants for completion of this application. The objectives for tonight are to be aware of available resources, learn from the mistakes of other builders, prevent accidents by learning what not to do, and avoid denial of your application for an airworthiness certificate. The overview: we're going to look at resources available, the basic process flow chart, and then we're going to look at each discrepancy before we wrap up the presentation. Before we look at the discrepancies, we're going to review hazard and risk assessment. And then as we think about hazards and risk assessment, as we look at each discrepancy. Let's look at the resources available to you. If you go to FAA.gov, across the top of the page, you will see 8 category buttons. And this slide shows the pilots and airmen category with the mechanics topic highlighted. Selecting the mechanics topic will take you to the mechanics landing page, which is right here. On the mechanics landing page, you'll have access to advisory circulars, which we're going to reference some advisory circulars tonight, airworthiness directives, type certificate data sheets, and forms. And there's a lot more on this page than just those items, but those are probably the most popular. If you select advisory circulars, several of the more common ones for aircraft maintenance folks and people that are building aircraft would be AC 43.13-1B and -2B, which are methods, techniques, and practices for aircraft inspection and repair, and also alterations. There's also AC 43-4B, corrosion control for aircraft, which is pretty interesting. There's a lot of detail in these advisory circulars. The AC 20-27G is for the certification and operation of amateur-built aircraft. This is one that you'll want to be very familiar with if you're going to build an aircraft. And I'm sure many of you are already familiar with it, probably more so than I am. FAA inspectors use Order 8130.2J as we look at applications and aircraft. Chapter 15 covers amateur-built aircraft. And here's an excerpt, and it encourages the inspector to provide these resources to you. There's mentions the advisory circular. There's also a link to the FAA's amateur-built website and your own Experimental Aircraft Association website. And I'm assuming a lot of the attendees tonight are in the EAA. If you select regulations at the top of the page at FAA.gov, and then you select handbooks and manuals, you'll find a lot of very good information there as well. And here's the handbooks and manuals page. And if you click on aircraft, there's about 4 volumes of the Aviation Maintenance Technician Handbook, and each one is 500 to 600 pages. Just a wealth of information, lots of color pictures and charts and information there for maintaining and building aircraft. In addition, there's the Plain Sense publication, which is good for aircraft owners. Now let's take a look at the basic process flow chart for certification of an amateur-built aircraft. And this is from AC 20-27. These are the first 4 steps. And my purpose here is just to show where we are in the process with this builder's application. First step is contact the FAA. The next step is to basically build the aircraft, design and/or construct the aircraft, then register the aircraft, and then mark the aircraft. And it gives you the reference where to find the information on each particular step. The next 5 steps are submit the formal application. That's the application we looked at. And we are here in the process where the FAA or an FAA designee inspected the aircraft and determined aircraft eligibility. So this DAR inspected the aircraft and found it was not in condition for safe operation, and so the application was denied. And the applicant was sent a detailed letter. The applicant was present during the inspection and was shown most of these discrepancies as they were found. When you submit an application You're also going to submit this eligibility statement, and it has to be notarized. And here the builder is certifying that a major portion was amateur built. That's in block 3. And it also states that the builder has records available to support that statement. The FAA has to verify your eligibility statement. And we do this by looking at your documentation to determine if you met the 51% rule. And this is just an excerpt from our order 8130 8130.2J. We're also going to verify the aircraft record supports the builder's statement in block 3 of the application. We're going to make sure that the aircraft record has a statement from the owner that the aircraft has been inspected. This is a certification by the builder that the aircraft was inspected and found to be airworthy. So you can see how important good documentation is for this process. And there's the statement that the applicant will sign. So at this point, the FAA or a DAR is going to inspect the aircraft to verify it is in condition for safe operation. And there is a sample checklist that can be used. It's in Appendix 1 in AC 90-89. And the DAR that inspected this aircraft really should be commended. And our DARs do a great job. And he probably saved this aircraft builder's life, as you see some of these discrepancies. There's just the cover page of that advisory circular. And there is the first page, portion of that first page of that checklist. So let's review hazard and risk before we look at these discrepancies. Once we see a hazard, we can try to determine the level of risk the hazard presents to an operation. Risk is the future impact of a hazard that is not controlled or eliminated. The level of risk is a combination of likelihood and severity. Likelihood is the chance of an accident happening from the hazard. Severity is the level of injury or loss that will occur when the accident happens. Once you know the level of risk, it all comes down to how much risk you are willing to accept. If you cannot accept the level of risk, you must take mitigating actions to eliminate or control the risk. So let's keep these concepts in mind as we look at the various hazards that were found on this aircraft. There is the risk assessment matrix with likelihood on the left side and severity across the top. And if something is probable that it will happen and the results of it happening are critical or catastrophic, then that would be a high risk. So here is our first discrepancy. The elevator control tube, it was located at the aft end of the cabin removable bulkhead in the floor area, is missing the cotter pin in the castellated nut. And this is definitely a hazard. This is a high risk because the nut is probably going to fall off at some point. And at some point, the bolt is probably going to come out. And once that happens, elevator control will be lost. And as you know, these types of failures usually result in a catastrophe and death. And let's not forget the acceptable methods of installing cotter pins, and that can be found in those references that we looked at earlier. It is a checklist item. If the checklist had been followed, flight control bolts and pins for safety. Our second discrepancy is the right elevator trim tab control rod is insufficiently connected to the input link. The pin is not secure and tab free play is excessive. The pin may be the improper diameter. And the DAR noted that on the left side, the rod end connection was a bolt with a washer and a lock nut securing it. So it would be interesting to know what the Bearhawk kit included for the connection. Was it a bolt with a castellated nut, or was it a pin as shown in this picture? So this is probably an example of failure to follow the manufacturer's recommendations. It's also when you're installing these critical components and fasteners, it's always a good idea to install the fastener such that if the nut or the safety comes off, gravity will keep the pin or the bolt in place. And that was also on the checklist. Trim tabs and rod ends for attachment. Discrepancy number 3 is the right flap torque tube. And the bolt is distorted and bent. And there was material removed from the head of the bolt, which is riding on a welded flange. And this same flange has been misdrilled at a different clocking location, which may affect the integrity of the tube collar's intended strength. I don't know how they even got the bolt through this hole as offset those holes are. It almost looks like the bolt had to be bent to get it through. And believe it or not, the left torque flap torque tube looked the same way. It's really important to use a center punch when you're drilling holes. And here's a picture from the National Archives, World War II era. Our next discrepancy is related to flaps. And when lowering the flaps with the handle, the flaps do not move symmetrically. The right flap actuation occurred before the left side began to move. Additionally, while viewing the flap cables, the cable tension is not equal and it appears not to have tension on either cable. The cable to pulley engagement does not occur until the flap handle displacement begins. All cables have a specification for proper tension, and this is critical for flight controls. And that's just a picture of a tensiometer. Next discrepancy was there were screws chafing the aileron cables. The left and right wing fairing strip attachment screws were too long. I don't have a picture of that. Discrepancy number 7, there was a foreign object in the wing. Inside the left wing lower access panel, there was a portable work light found. Now, tool control procedures are very important. And some ways to prevent foreign object damages and hazards are keeping the area tidy, shadowing your toolboxes so that you can easily see if something is missing, Do a post-work inventory of your tools and equipment. And lastly, inspect the area before you install the panel. These simple things could have prevented this, because when you have a foreign object floating around, obviously it can jam a flight control or something of that nature. Next discrepancy, hardware could be heard rolling around when the ailerons were deflected. I don't have audio available, but you can imagine anything inside a flap or aileron is going to make a lot of noise. It's important to use all your senses, sight, hearing, feeling, and smelling, when you're working on aircraft and when you're inspecting aircraft or building aircraft. Certainly, the applicant could probably have heard this foreign object just as the DAR could hear it. In fact, almost all of these discrepancies were pretty easy to observe. Discrepancy number 9, engine control mount plate holes. They look like Swiss cheese. And the spacing is less than 1 time the diameter, which might lead to cracking between the holes. Advisory Circular 43.13 provides details on rivet hole spacing. I think this is actually an excerpt from one of those handbooks I showed you on FAA.gov. Some of the different problems with rivets. And there's information in there on rivet spacing. And if we look closely at these specifications, we'll probably see more problems here than just the spacing. Discrepancy number 10 was the engine throttle cable control was loose. This clamp could be moved back and forth very easily, and this affected the throttle position. And engine controls are one of the top 3 causes of accidents due to maintenance errors. And this loose clamp could result in a sudden loss of engine power. Also, keep in mind that long runs of these types of cables without supports can result in inadequate control of the item. Next discrepancy, the carburetor safety wire. The engine carburetor aft side screw has a screw that is not safety wired in a tightening direction. It's actually hard to see from this picture. Discrepancy 12, the oil filter safety wire is incorrect. It's not in a tightening direction. Now that one is very easy to see. So if the oil filter loosens up to the point where the engine oil leaks out, it can get really expensive. And it's also very dangerous when the engine seizes up, especially just after takeoff. Sometimes the phase of flight that something occurs can be a big factor on the severity of the injury or loss. There's many examples on how to properly safety wire fasteners. Here's another one. The cabin heat control was improperly safety wired. And the DAR wrote that the set screw safety wire was not secure and is not in a tightening manner. Same connection viewed from the top has internal threads showing that indicates the journal connection is not fully engaging the mechanism. So I'm going to show you a 57-second video on safety wire. I think you'll find interesting. Hopefully the internet signal will be strong enough to do this.
I'm here today at the Tennessee College of Applied Technology Aviation Campus at Memphis, Tennessee to talk about safety wiring. These are safety wire pliers, and they're used by mechanics to ensure that the bolts in our aircraft are safety wired properly. So what do we look for when we pre-flight our aircraft in regards to safety wire? We'll talk about that on 57 Seconds to Safer Flying. Safety wire is used to keep a bolt from backing out due to vibration. May 2018. A Cirrus crash lands just after takeoff in Texas. The pilot survived to tell investigators that he was having an uncontrollable left roll. Inspection of the wreckage revealed that the left aileron actuator arm and attach bolt were missing. The remaining actuator bolt was missing its required safety wire. This bolt is easily visible during a pre-flight walk-around inspection. This is a separated aileron cable from a Bonanza. The safety wire held firm and the pilot didn't even know he had a problem. Learn to tell the difference between a good safety wire job and a poor one. Lock nuts, castle nuts, turnbuckles, and cotter pins all help hold your airplane together. A Glasair crash landed in Arizona 30 minutes into the flight after the engine lost power. It turns out the cotter pin, connecting bolt, washers, and castellated nut were missing from the linkage to the throttle arm. It's not always easy checking them all. So learn by doing a walk around with your mechanic. So get familiar with where the safety wire is on your aircraft and make that part of your pre-flight inspection. For the FAA safety team, I'm Phil Dixon.
All right, hopefully that came through. The next discrepancy on the list was oil cooler fitting was loose, just finger tight. Discrepancy number 15 is the engine tachometer cable was loose. Now the risk here is probably low because this would probably result in an indication problem and not a hurt or loss situation. So as we think of the hazards and the risk assessment, some of them obviously have a higher risk than others. Discrepancy 16, the engine shroud upper side has a misaligned hole with no fastener installed. And as we know, engine shrouds and baffles are important for engine cooling. And here the starter solenoid cable was loose. It easily moved with hand pressure, and this was demonstrated to the applicant. If you think of the hazard and risk process, this hazard might be a lower risk because the problem will probably occur during engine start on the ground, which is less severe than something that occurs in flight. Here's a discrepancy where the oil line was chafing, and this was a metal-to-metal contact. And this can result in a high vibration, high frequency vibration that can actually loosen that connection. Here's an engine baffle mount screw that was loose. And here's the upper wing attach fitting. It looks like there's some grinding wheel marks here. The applicant stated that there was a washer welded to the bracket that prevented installation of the wing. The applicant stated that he modified the kit by removing the welded washer and added additional material to the outside of the lug. Now, the records did not clearly indicate the details of how this was done, how much material was removed, how much was added, so on and so forth. And wing attachment, of course, is a high level of risk if it fails. So this could be one of those that is a high risk item. The builder also did not have adequate documentation to show compliance with the 51% rule. And The documentation has to support the requirements of the regulation and the FAA order, which is used to ascertain what was fabricated, assembled, and inspected, who performed these actions, the date the activity was performed, where the activity was performed, the methods used, and any commercial assistance or educational assistance that was used. And here's a portion of the fabrication and assembly checklist in Appendix 8 of the advisory circular that helps document all these things. And it's really easy now with digital technology to support all of this with the digital pictures. So let's summarize and review. Today, we reviewed hazards and risk. We looked at where to find resources for builders. We looked at and saw the missing cotter pin on the castellated nut, and this would cause a loss of control. We saw where incorrect hardware was used, a pin and a cotter pin instead of a bolt and a lock nut. We saw a lot of things were safety wired improperly. We saw the loose engine control clamp, which could cause a loss of engine power. We saw some items that were chafing. We saw loose electrical connections. We saw foreign objects inside the aircraft. And lastly, we saw insufficient documentation, just not enough evidence to meet the 51% rule. So from one end of this aircraft to the other, there were discrepancies. Some of them were higher risk than others, but it all leads to the conclusion that it just was not in a condition for safe operation. Our FAST team website is FAA safety.gov, and I hope you'll use it often. Go under the maintenance hangar and pilot tabs to see all the information there. Participate in WINGS and the AMT awards programs. Best way to learn about these programs is to look at the tutorials that are on the website. And I hope you were all able to view this entire presentation. And that's my name, email, and contact information, as well as Ryan's. If you want to take a picture of this screen. If you have any questions, I'll do the best I can to answer them. And I'll look at the chat now. Somebody asked if this was a scratch-built Bearhawk, and I don't know the answer to that. I don't have the background, a lot of the background on the particulars. I do appreciate the interest. And I want to thank you all for attending tonight, and especially for hanging in there after we had the technical glitch. I really appreciate that. And until next time, signing off, this is Gary Mitchum with the San Antonio FAST team.